My name is Marshall Cox. I'm the founder and CEO of Radiator Labs. I'm going to tell you about steam heat, which is always a super exciting topic. So first of all, steam has a lot of problems. We all know this who have lived in an apartment or a house in New York City in particular. And the problem isn't with steam. Steam is actually a pretty awesome technology. It's been in these buildings since they were built, often hundreds of years ago, 100 years ago, decades at least. And they're super overheated. And the problem is that it's very hard to control where steam flows from the building. And you can try to do that, and they were really well balanced when they were built. But then the biggest change that we've seen is that we've invented and nearly universally retrofit windows to double pane insulating glass, and that completely changed the balance of our buildings. And now you have apartments that are cold and need a lot of heat, and people who are super hot and open the windows as a result. Obviously, people are really uncomfortable because of this, so it's a problem for tenants. It's a problem for maintenance staff because these things are hard to maintain. But it's an enormous financial and ecological disaster. About $7 billion is wasted every year in the 10% of the US residential housing market that uses steam as a primary source of heat. In New York City alone, it's $1.2 billion. And you can imagine literally taking $1.2 billion of fuel and burning it in the streets. That's essentially what we're doing every year. I want to get some perspective on this problem. So steam has been around for a long time. It's been around for approximately the same amount of time as the phone. So this is Alexander Graham Bell. He invented the harmonic telegram, which is here. And think about how many changes have gone through that technology in the past 100 years. We all have supercomputers in our pockets now. The amount of change is dramatic. In contrast that with steam, it's not necessarily a fair comparison. We have new, better heating technologies. But the radiators that have been in these buildings haven't really seen anything happen in the last 100 years. And this is particularly relevant here because this is Alexander Graham Bell standing next to a radiator. And I can guarantee you that that building is probably still here and that radiator is probably still there. These things have been installed for literally a century, sometimes more than a century. And they still work, which is amazing, but they have a lot of issues. So I got my PhD at Columbia University. I invented this technology there. I did not have anything to do, my research had nothing to do with steam or radiators, but I lived in a unmitigated hellhole apartment. It was super hot. I invented the technology, worked really well. We went to compete at the MIT Clean Energy Prize, won that, which was amazing. That was essentially the beginning of our company. We developed a full building system and iterated over the past few years. And most recently, NYSERDA has supported an evaluation of that technology in a bunch of buildings. I'll talk about those results later. It was very good, and we were really excited about what we're doing. So briefly, what are the things you can do to solve this problem in overheating in buildings? Most people have tried to address this from a plumbing perspective, but steam is a 100 degrees Celsius gas. It's very caustic when it condenses into water, and you're talking about a two-phase distribution problem. It's really hard to control that kind of distribution system with a valve or other kinds of plumbing solutions. It doesn't really work. We've approached it from a different direction. We actually control the area around a radiator and thermodynamically manipulate the steam flow within a building by doing that. It has the benefit of being easily installed. You don't have to have any contact with plumbing. It's especially nice not to have to mess with 100-year-old pipes. And it works really well. Every one of these systems has a wireless radio. We communicate data in real time to the cloud. That lets us learn how buildings heat up and cool down and optimize that heat generation on a building-by-building basis. It also lets us connect this data to people's cell phones so they can control their temperatures, even setting setbacks and different time-based things you can do with a normal thermostat. This is a level of control that these buildings have never had in their entire history. So it's a pretty big deal for the people who live in these buildings. These are those results I told you about from NYSERDA. 7 buildings in the past 5 years, we found 25% average savings. Maximum savings was 45%, and I just want to point out the minimum savings over there, 15%. That building is a LaFrac building out in Brooklyn. It is now the most efficient single-pipe building in all of New York. So even in buildings that start out very efficient, we can still save a lot of energy. There's a lot of waste here to be. To put this in perspective for income for a portfolio, if you can save 30% of your heating costs, that translates into a net operating income increase of 10% because 30% of operating costs are often in heating the building itself. So that's a big deal for portfolios. Now I want to transition to talk about data. The first thing, the most obvious thing, is what can you do with data in real time in a room? We take temperatures and we obviously feed back that temperature into our system to push heat out into a room when it's needed. That allows us to do away with the drastic overheating and underheating that you get in these kind of buildings. This is real data. You basically turn an apartment into a flat line temperature at your set point. It's a very important and nice change. My apartment obviously has these installed. You can get a little deeper into the data as well, though. So in most bigger buildings, you have what's called a two-pipe steam system. And every radiator has a steam trap at that point. And when we install in buildings, we typically find that about 25% of the steam traps are blown and malfunctioning, which means the steam is flowing into the condensate line being wasted. Every broken steam trap wastes about $200 to $400 a year. So you can see how this adds up very, very quickly. We can use the data that we're gathering to analyze steam trap health in real time. And you can imagine that maintenance programs in buildings, it's hard to measure this stuff because it's in someone's home. We can just do it in real time, remotely, and tell people when things break and they need to be fixed, which increases dramatically the maintenance efficiency of portfolios. Okay, so very quickly, digging deeper into the data, there's some really interesting things here. If you can look at this, on the left these are two buildings, top and bottom. On the left is before we installed, and on the right is after we installed. Each one little block in these graphs shows an apartment that's been categorized by temperature. So the red blocks are apartments that are saunas above 82 degrees. The blue blocks are apartments that are freezing below 62 degrees. And you can see that before we retrofit, there's a pretty even distribution of very hot apartments and very cold apartments. This is what you'd imagine seeing in a building. After retrofit, if you could see the green here, we've dramatically increased the number of green apartments. So most of the apartments now are comfortable. Of course, there's still outliers on the hot and cold side. And so this is on first level to point out that our technology is awesome. It works really well. But this is a very rich data set. Of the apartments that are still hot, why are they still hot? It turns out that we can do some interesting cluster analysis and apply algorithms to this data to figure out what characteristics those apartments share. So maybe they're on the top floor and the roof is uninsulated. Maybe on the bottom floor and there's infiltration problems. Maybe they're all on the north side and don't get sun. You can essentially figure out what's wrong with these buildings that no one even knew existed. And that's interesting because you can take that data, we control the boiler. We know how much fuel you'll save additionally if you fix that problem. And then if you know how much that problem costs to fix, you can calculate a pretty accurate return on investment. And that basically will unlock a significant amount of capital. People want to fix their buildings, but the capital to do so is not really available because no one knows how long they're going to take to pay back. No one knows how much they're going to cost to fix. No one even knows what the problems are. So what we're trying to do here is take the data that we're gathering to figure out what those problems are, figure out how much it's going to cost to save, and unlock that capital to fix the big problems in our infrastructure, which is primarily located in our older buildings that no one has the time or money to evaluate properly. And we have a big grant from the National Science Foundation to do this. So we're pretty excited about what we're doing, and thank you very much.